So today we are going to talk about, you're going to be able to determine when work is done and when it is not, calculate how much work is done by a force, discern when work is positive and negative, describe and calculate the power in terms of work, also be able to apply the work energy theorem with kinetic energy. So here we go. Give that one a shot. Tell your neighbor. Correct answer is B. You are exerting force. Yes, you are. It might be difficult. It might be a heavy thing. But if you're not moving, there's no distance. No work is done. Okay? It's not until like you move it is work done. Okay? Good with that? Give that one a shot. Probably want your calculator. Yeah. Seriously. Yeah. So your free body diagram looks like this. Okay. So work is equal to force parallel times distance. Okay. What part of force of tension is acting parallel to the direction, the distance, or the way it's being moved? Yep, FTX. Does that make sense? So in this scenario, we are looking at FTX times the distance. So FTX, use cosine of 60, is equal to FTX. 600, this is 1/2. So the work done by tension is equal to 300 newtons times 20 meters. 6,000 joules. How do we do? Zach.
600 is a force of tension. No.
Yeah, 600. 600 is the force of tension. And then I found the x component of that. Ready question, or is that a stretch? Okay. Good with that? Questions there. So a popular question that comes up is like, well, what about friction? Like, you didn't even touch friction. Doesn't that like mess with stuff? It does, and we'll incorporate it later. But this question was just asking how much work did tension do? And that's it. Okay, so read the question carefully in terms of what it's asking for. Okay, the work done just by tension. Good? Have a conversation.
It just depends if it's still sliding. It's not moving. Well, there's the frequency. Oh, wait, never mind. Mr. Smiley, does gravity do work?
You can. In this scenario, we'll talk about it.
But how many of those do work? If I pull my phone, if I pull smart, if I understand, no frictions. If I pull my phone right now, there's no force to do. It's like what's making it move, what forces it to. This is not.
Okay. What do we say? Okay. How many forces are acting on the box? 4. Gravity, normal force, applied force, and friction. Okay. How many forces are doing, well, which forces are doing positive work? The thing sliding down the ramp. Which forces are doing positive work? Which force has a component that is acting in the same direction as motion? So we're tilting our axis. FGX is going in the same direction as motion. So force of gravity is doing positive work, at least the X component of that. Okay. What forces are doing negative work? The forces that are acting in the opposite direction of motion, applied and friction. You okay with that? Okay. How much work is normal force doing? Is there any component of force that is acting parallel to the direction of motion from normal force? Is any component of force that's acting parallel to the direction of motion for the normal force? So it's acting perpendicular to the direction of motion? It is, so normal force does no work. Okay? Correct answer is D. There are 3 forces doing work. Force of gravity is doing positive work. Applied force and friction are doing negative work. Okay? You all right with that? Now, big picture, why are we bringing up this new concept of work? Like, what's the point? So, you have been studying energy in science since like late elementary school. Energy cannot be created or destroyed, right? And we have not yet talked about energy in this class. Okay, it's a big part of science. So the question brings up, well, I bet you force affects energy. Like if a force acts on an object, that'll probably affect how much energy the object has. Yeah? Okay. So we've baked up this idea, this concept of work to help us grapple with that question. Okay. Because work and energy go hand in hand. So that's why we're bringing up this whole notion, this new concept of work, because it tells us how force can affect energy. Okay. So we're back dragging our box. Tell your neighbor.
So my tax spreadsheet still do positive means just there.
Correct answer is okay. Is friction acting parallel to the direction of motion? Yes. So we don't have to take any components. Is friction acting in the same or opposite direction as motion? Opposite. So doing negative work. Are we good with that? Okay. So you got 200 newtons times 20 meters, 4,000, and the fact that it's going the opposite direction, motion, just plug that. Good? Same scenario. Tell your neighbor. Correct answer is? Correct answer is D. Why? It's acting parallel to the direction of motion. Sorry. It's acting perpendicular to the direction of motion. Good? Okay, what about normal force? How much work is it doing? 0 as well. Okay? So on a follow-up question. May I remind you, tension did 6,000. Friction did negative 4,000. Correct answer is A, 2,000. So you can either find the net work, bless you. By the way, I just kind of led you to do it. You add up all the works done. Okay, so we had a positive 6,000 plus a negative 4,000 plus 0 plus 0. Okay, gave you 2,000. Or, which is equally valid, you could find the net work, sorry, the net force times your distance. That's also equal to the net work. We kind of did that sort of. So that would be equal to, well, we'll do it this way. Force of tension in the x direction minus friction times distance. So we had 300 newtons minus 200 newtons times 20 meters. We'll still get you 2,000 joules. Good with that? Okay. Either way is fine, whichever you prefer, your preference. So, power is equal to work over time.
That's great movies.
What?
Great movie.
Yep. Thumbs up when you have a guess. Any guesses? Out. All right. So I need to figure out my work. I've got my time. Okay. So work is equal to force parallel times distance. I've got my distance. I need my force. That's the free body diagram. The fact that you're going at a constant velocity because the sum of the forces in the y direction are equal to 0. So from that, you know that your applied force is going to be equal to your weight. And to find your force of gravity, you're multiplying by 9.8. In this case, we'll multiply by 10, just to keep it easy. So yeah, 50 kilograms times 10 meters per second squared. So force of gravity is roughly 500. Stick that in there. So we have applied force is also equal to 500. Stick that in there. So work is equal to 500 newtons times distance of 2 meters. So work is equal to 1,000 joules. And power is equal to 1,000 joules over 0.25 seconds. Here are that. Okay. Hello, your neighbor.
Just out there. How does he have the best grade in this class?
I don't.
I'm pretty sure you do.
No, I don't. You guys are mine.
It got pretty close to
I think Hannah probably has.
it. Out of us three right here. Yes, sometimes you make me question your text.
With the time it took for him to push it 40 meters, he just doubled it. He played golf.
You double. Okay. Before we answer the question, which person did more work?
They're the same.
Which one did more work?
Oh, I thought you said hour.
Okay. Palmer did more work, but which one's doing work at a greater rate? They have the same rate of work being done. Palmer just did twice as much and took twice as long to do that. You all right with that? Okay, so they both have the same power demonstrated. Okay. All right, so we are revisiting Dragon the Box. Okay, and I want to know how fast the box will be going after 20 meters if it started from rest. Now, all things like revealed, you could do this same problem with what you already know how to do. Free body diagram, some of the force in the X and Y direction, solve for acceleration, stick it in a kinematic equation, and get the right answer. Okay. I'm going to push you to do it the working energy route. Okay. So the question that usually comes up is like, well, why? Like, if I already know how to do it, like, so there are circumstances where work and energy shine that free body diagrams and kinematic equations fail us. There are times when the kinematic equations are like, yeah, I was born for this, and working energy is like, ugh, I got nothing. Okay, so you got to be able to dance between those. They're two different sets of tools to do different jobs. Okay, so in this problem could be solved by either. So we're going to look at the net work is equal to the change in kinetic energy. Okay, which is final minus initial. We've already calculated what the network is in this problem. Okay. So this was 2,000 joules. We already found that out. Okay. So this is 1/2 mass times speed squared. This cursive V is speed rather than velocity. So we don't have direction. So this is going to be equal to 1/2 mass times final speed squared minus 1/2 mass times initial speed squared. Okay. If it started from rest, how much kinetic energy do you have initially? 0. You all right with that? So you have 2,000 joules. It's equal to 1/2 mass of 50 kilograms times final speed squared. So you have 2,000 divided by 25 takes the square root of 80. So that's 8.94 meters per second. You would have gotten the same result if you would have done a free body diagram, found the acceleration, some of the forces in the x and y direction, plug that into a kinematic equation, your final velocity. Okay. Again, there are certain scenarios that work in energy are like, yeah. And other scenarios where free body diagrams like, I got this. Sometimes it could be either or. Okay. On the final exam, you can pick. Okay. Tell your neighbor. Okay, to find the net work, you could either do force, the net force times distance, or you can do change in kinetic energy. I did not give you enough information to go this route. Using change in kinetic energy. Okay. So, you okay with that? So when you're doing this, one of the reasons I brought this question to the table here is because I want you to be careful of order of operations. Make sure you square the speed before you subtract. So you get 9 here. Okay. Times 50, so 450 minus 50, 400. Good with that? Make sure you square it before you subtract. Good? Have a conversation.
Yes, because the next part is going to be, we're going to find the tension. Because the next problem, it actually isn't. Oh, so there's no. You don't. Well, I was assuming that you just.
Correct answer is you can find the net work. But in this scenario, you don't have, there's more than one forces contributing to the total work. If tension was the only thing doing work, then yes, you could do it. Okay? But there's other things going on, like friction. They're doing work. So recognize what this equation gives you and what it doesn't. You cannot find the work just by tension. You can find the net work total, but to find the work done by just one force with this, there'd only be one force doing work, or you could find, you'd be given stuff about friction. Exactly. I told you what friction was. Okay, so the very first problem we did, like dragging this, I gave you friction.
But we solved the work without friction.
Oh yes, that's true. I changed the scenario. You got 100 kilograms. Like it's a different. There's different numbers. Okay. Last question. Have a conversation.
I also think that yeah, but like I think that the so hard
Correct answer is
I'm gonna guess E. Final answer.
C. Crazy cat. Great question. So the net force in this scenario is FTX minus friction. Friction is greater than tension in the X direction. That quantity is going to be negative. Negative work. Okay. Here, net work is equal to the change in kinetic energy. Oops. Sorry, that's an initial. If you're going slower than what you started, there's going to be less kinetic energy at the end than what you had at the beginning. Good with that?
And the friction is larger than the tension. It's so dramatic.
Oh yeah. You're just slowing down. Let's say you went from like you're dragging it across like the sidewalk, and then you went into like sand or something. Oh, that was awesome.
What was the
Yeah.
acceleration of that?
That was crazy.
If you also go plus the negative 9.8, if you would count for errors.
Positive and negative, those are directions, right?
No, but he's filming the left.
So,
I was thinking there's
good question.
while he was filming the lesson.